in the AI data center solutions and reporter Praful. Today, I'm going to talk about how to maximize, AI cluster performance using Juniper's self-optimizing networks. So I know earlier you had asked like how can you show a topology? So let's look at what are the challenges? How AI application traffic differs from traditional data center, right? So most of this Rocky is over UDP, and also what happens is there is very low entropy. So there are very few flows, they're bursty flows, high bandwidth, and some of them live throughout the training, right? So that's the first challenge in the property of the flow. And the second one is if you see training, when you parallelize it over multiple GPUs, hundreds of GPUs, one kind of parallelism is data parallelism, which is very popular. In that case, GPUs are lockstep. So they all load their batch of data that they're going to train on. And at the end of that iteration, they have different gradients that they have to synchronize amongst each other. And until they do that, they cannot move to the next batch. So they're kind of idle. So that's why there is that synchronous compute during training that even exacerbates this problem. So a single flow that is delayed in this synchronization could really keep a lot of GPUs idle. So that's why job completion time is a key metric. Now, in this diagram above, what you see is it's a physical topology strategy that you say, hey, I can ease the burden of my load balancing. So this is NVIDIA has been prescribing this, and it's called rail optimized. So the first NIC of every GPU has its own NIC, and the first NIC or first GPUs are connected to the same switch. So there are 8 GPUs in the DGX form factor or similar, and you see 8 switches or 8 rails being created, and then you have the spine layer. In the leaf to spine, there is 1:1 or subscription to just handle this capacity. And these are physical topology strategies that will give you the best chance on to keep the performance up. Now, Praful alluded to this, and he said he mentioned that in the traditional or Ethernet or what we call static ECMP, that catered primarily to most non-AI applications that were built on TCP. And TCP said, hey, just give me in-order packets delivery, right? And that was because TCP has this exponential back-off whenever packets are out of order, and also it has a slow start. So the bandwidth hit whenever that happens is pretty bad. Whereas in Rocky's case, there is no slow start. There is all these flows are always bursty. They come in and are long-lived. So the traditional Ethernet, which was like do a hash and pin a flow for its life cycle on a path, which was TCP's main ask, worked well in that space because there was so many flows, there was enough entropy, some long-lived, short-lived, so a natural distribution or a random distribution worked well. In this case, if you apply that, you can get in, even if you have 1:1 or subscription, you will get in trouble where you can make forwarding decisions or load balancing decisions at the leaf and oversubscribe a leaf to spine link, or 2 leaves independently sending traffic could overload a spine to leaf link. So really what we need is more efficient load balancing that is designed for handling Rocky traffic. And again, Praful mentioned this, that congestion can really bring down the performance of these AI workloads. Again, because a single flow delay can cause that. And so that's why avoiding that congestion, because you have enough capacity, is the key strategy for maximizing performance. Now, if you see here, like I've just said currently, and there was a discussion in the previous session as well, like if you see packet spraying appears to be the current best method of load balancing, and there is truth to it. So if you see SmartNIC-based solutions where these flows hit the first leaf, and then the packets are sprayed across all the ECMP paths, and then they are delivered out of order to the NICs. So you need specialized NICs or super NICs today, which can basically handle those out of order packets. And the other thing is, the other approach is distributed schedule fabric, where same thing, flows hit the first leaf, then they are sprayed over just like you do it in a chassis-based fabric solution. There's a credit grants-based mechanism, and then packets are basically sprayed to load balance across spine. But in this case, some of them chop it into cells, some don't, and they would reorder these packets, because again spraying will cause out of order, but they will reorder the packets before they ship it to the GPU NIC. So in this case, of course you need deep buffers to enable that, and if you compare, the cost is again, both of these solutions are expensive. The super NIC ones, now you need specialized NICs, which are more expensive to begin with, but are also more expensive in terms of they consume more power. And already these GPU servers or racks are power constrained. Now you're adding almost 400 watt more power to each server using this. And on the second one, yes, of course, these leafs are deep buffer, and hence they're more expensive. And also both of them are proprietary. So you are logged in a on the left-hand side, you will be using vendor A's proprietary NIC to achieve this. And so you'll be logged into any expansion of your AI data center because of that. And also in the case of the distributed schedule fabric, you are definitely logged into that the whole fabric ecosystem there from a single vendor. So now let's look at, Praful mentioned this in the previous session, but I'm going to go dive it a little bit deeper, that how Juniper's open and standards-based approach using Ethernet solves some of these problems. And the umbrella, we are calling it AI load balancing. So the first technique is dynamic load balancing, right? So this is an evolution or enhancement over static ECMP, where we take more informed decision. Instead of just doing a hash and randomly pinning a flow on on one of the available paths, we track almost at every microsecond granularity that, hey, what is the link utilization, or what is my link quality at every leaf where the first this traffic hits, right? So as you can see, the most opportune point where you can take a good load balancing decision and avoid congestion is the first leaf, because it has the most available paths. So what we do is we track link quality, which is a function of how much traffic is going. So link utilization on every link, we track that, and also see that, hey, is there any buffer pressure on any of those links? So those two metrics are combined, and we derive link quality. And here I'm just showing for simplicity three bands, but there are actually 8 bands of link quality. So we classify every link from a 0 to 7. And when actually these flows come in real time, at that instance of time, at a microsecond granularity, we say, hey, which is the best link based on this link quality available? And we start placing the flows there.
Hey, Denise Donnie. Who's making that decision? The switches, the leafs themselves?
Yes, so this is all in the ASIC logic. So this is done real time at line rate. Yes.
To follow up on that, is to what Denise is asking there, where's the state being managed, right? I'm monitoring the flows. I'm holding on to that information. Is that some sort of packet broker or Docker container running on the leaf or the spine? What's handling that or managing all that flow?
Yeah, so this is none of that. Because these 800, so this is like, let's say our current generation is 64 by 800 gig. And when all of them blow up, you have no time to, so this is all burned in the logic in the ASIC itself. So these decisions, along with our Juno software, is actually a function of that. So that's why it's a non-blocking switch. It can, if all 800 gig 64 ports blow up, this can do all this at line rate for all of those. And that's the only way, because otherwise you'll introduce delays and you can get in trouble. So so there are certain so 2 primary methods on how you do this, right? So as I said, these flows are long-lived and very few of them. So to extract more entropy, the first one is flowlet mode, right? Now, what the flowlet mode does is extracts more flows or subflows in time, right? So if a flow pauses for a configurable amount of time and the next burst comes in, we can treat it as a new flow, even though it's like the same 5 tuple, right? In the traditional Ethernet. So that way we can break these flows into more subflows and then start, fairly distributing them based on that instance of time, whatever was happening. And this works very well for AI workloads because, in AI workloads, there is this natural tendency of compute and synchronize. So all the GPUs that are participating, let's say in all reduce, they will load their batch of data, and as I said, they're lockstep. Once they're done with their computation, they will synchronize. So there is a natural pause, and that fits very well in this. And this doesn't introduce any out-of-order packets because, the previous burst or a previous flowlet in this case, if we placed it on a path, let's say to spine 1, and the next burst after waiting, let's say 20 microseconds or 16 microseconds, we place it on a better path at that instance of time. The previous packets would have reached the destination. That's the assumption. That's why you shouldn't see out of order packets. Now, the second mode is packet mode. As the name suggests, you can see we make this decision on a per packet basis. So this is the classical packet spraying. So we will spray the packet across these ECMP paths. We will still factor link quality in it. So if some link still gets degraded, we will avoid that link even spraying. But this is packet mode.
Quick question. Sorry. Because now you say every switch will make that decision. We have those two modes. But if that leaf one switch will make a decision, I will go through S1 or S2 or S3. They need to be aware of each other. Is there some kind of a stacking mechanism between those switches or not?
A great question. And that's the next technique, that is GLB, that actually takes a global view. In this one, I'm just going to say, so this one is effective. Yes, you are right. These are based on local decisions, local link quality. And you can still send some extra traffic to a spine, and that the GLB will solve that problem. But
Well, we're still on the local, Brian Martin here, Signal 65.
Correct.
For the flowlet mode, those periods of inactivity, you mentioned 16, 20 microseconds. Is that tunable? Is that something so we can set that?
Yeah. So the lowest you can go is 16 microseconds, and then anything up to, you can do that. So this basically solves, if you see this picture, this solves this problem, right? The local, you're gonna fairly distribute traffic over all the leaves, and you will avoid getting overloading a single, because you're now tracking each link, right? But the other problem is still there, and I'll come to your question, right?
What does ECMP stand for?
Equal cost multipath. So
Okay.
So because these are symmetric flow architectures in data centers, so a routing protocol will build all the paths that are equal cost, and the leaf will pick one of them based on a load balancing that you choose.
Okay. And since we're right here, what is IXIA?
Oh, IXIA is a traffic generator. So
XCF. Okay. Oh.
So so here what we did is we in the lab that we have here with the NVIDIA GPUs, we put these three techniques to test, right? So the first one is static ECMP, that's the hash-based ECMP, DLB flowlet mode, and the DLB per packet mode, that's the packet spraying. And we used a ML common standardized benchmark DLRM for this test. And what we found is, the static ECMP deteriorates sorry, one more thing is we use the XCF traffic generator to introduce congestion so that we can see the performance under congestion, right? So as we increase the load on the traffic generator, started introducing more and more congestion, you see that the static ECMP starts to deteriorate. DLB was very deterministic, highly deterministic, and it actually did pretty well as there more congestion was introduced. Best was still packet spraying, as you can see from that, the 37.5% number, but it was only by a margin of 0.08%, right? So the flowlet really did well without you needing any special NICs to handle, or expensive NICs to handle this. So really, there is not that much of a ROI on that, right? And if you see pictorially, this is a graph that shows you what was the link, how much traffic was going on all the paths between leaf and spines, right? So as you can see, static ECMP, it was a random distribution. Some links were highly utilized, some were not. Whereas in DLB flowlet, you see all the links are fairly utilized. And that explains the performance predictability. And the packet spray also looked exactly like it's indistinguishable. That's why I don't show you, but that's how it looked like. Right? And in terms of variability, so the number of times, so this is a graph on, we did 3 consecutive tests, and this is a nickel test, which is a standard NVIDIA open source tool. And you can see the variability in performance of static ECMP, which is basically lottery based. You're picking a path. One time it got really lucky and had really peak performance, but the next time it was 196, and third time it was around 263, right? So, and this is in a controlled environment, whereas in real clusters where the multi-tenant traffic is hitting, this variability can really hurt, right? Whereas the DLB really reduced that variability band to a very narrow one, and you have 373 to 353, which is really good. Now, coming to the global load balancing. So the second problem is still based on local decisions. DLB or these leafs can still send some traffic where, even though you have built an equal 1:1 capacity, because of these local decisions may skew some traffic or, can create imbalances by sending traffic to a spine. And in this case, what we do is, so for the DLB, the ASIC already calculates all of its local link quality. In GLB, what it does is it actually sends it one hop of upstream, or in this case, the spines are going to send that link quality data that they're measuring locally to these leaves, right? And now these leaves, because the first leaf is the most effective point of where you can take a good load balancing decision. At the top of the tree, you pretty much have only one path down, right? So that now these leaves are armed with that information. So what they do in the example that you brought up, so let's say GPU 2 is going to talk to GPU 6. What the leaf does is first it refers its local link quality and says, okay, one of the links to spine 1 is already a lot of traffic is going there. I will avoid that, but I have two paths now, right? To spine 2 and spine 3. And if it was only DLB, it would have picked one of them, right? And in this case now, it is armed with this information that spine 2 told it like, hey, one of my links is congested. So in this case, the leaf 1 is going to say, okay, I'm not going to send traffic that way because I have a clean path all through via spine 3. So let me load balance this new flow onto that path, right? And 2 things need to happen here. One is an ASIC to ASIC real-time update, that's updated. But one more thing we have done is we have an IETF draft, which we have published on, enhancing BGP, where now we are tracking next hop, right? So these leaves, and that's done like in the control plane. It doesn't have to be in the runtime. So each leaf knows, like for every destination leaf, which flows may take which path, because let's say when the real-time update comes from S2 says, hey, my link to S2 and to L3, that one in the red, is congested or is highly utilized, then it needs to determine which flows may take that link, right? Because it still needs to send all the traffic destined to other 62 ports on that spine 2, still to spine 2, right? So that's how we just determined that by the BGP's next hop tracking on the leaf, and then when the update comes, we just pull those routes out, and so for the temporary time being, the traffic will not be sent to that spine. And when we get the next update, and if that link is fine, we just restore them, and then load balancing is restored. Yes.
So I think back to the earlier question about what's handling state. I think you just answered that, right? We're moving that into the BGP control plane and saying, correct, hey, BGP is going to advertise, keep up with what's available, what's not available. Any potential performance hits from that perspective? I mean, it sounds like that might be a lot of BGP updates unless we're looking at very similar traffic types in this cluster.
Yeah. So BGP, we're relying on BGP to learn the paths. And also we have done this enhancement to know, hey, not just next hop, I need to now know, hey, what next hop, so which links. So that's done maybe when even training has not started. So you build this and that's fine. In the runtime when traffic is running, there is a ASIC to ASIC GLB update, When that comes in, I just refer to this table and say, hey, spine 2 has reported me this link is down. What did BGP tell me? Which destination may take that link on that spine? We just take that out and put that way. So BGP really is not in the runtime. So there is no reliance on BGP update to this. There's a GLB update that's mapped to already built topology information that BGP was used for.
Gotcha.
So this is like, as Praful said, like a Google Maps, right? Like, so it gives you end-to-end visibility, not just like, hey, what does my freeway look like right now, but what's the next connecting freeways?
So Google Maps is a good analogy there, because the color can go from blue to yellow to red to black. I see low and high there. What's the granularity on those paths?
Great question. Yeah. So again, so here just to explain, I had three levels. It's actually 8 levels.
Okay.
So 8 bands of quality are there, 0 to 7, and that's what is used for DLB decisions as well as GLB decisions.
Thank you.
So now then, so these two are quite effective at actually solving a lot of congestion. And as you can see, they're dynamic because they're reacting to wherever congestion is created in spite of, you fairly distributing the flows. And then we at Juniper, we try to challenge ourselves like saying, hey, is there a simple and better way to actually avoid congestion, right? So this RDMA-aware load balancing, I'll just take a moment to describe it. Now, whenever the training is occurring at the fundamental level, whenever the GPU needs to write something or synchronize its gradients or whatever it's doing over RDMA to another GPU's memory, at the fundamental level or lower level, what happens is, so these are orchestrated by a middleware called Nickel, which is communications library from NVIDIA. And it sets up like these, the analogy could be like these sockets in the TCP world, right? But these are created by a middleware and then reused over time. So what happens is there is a memory region associated on, let's say the left side is the sender GPU, and then there is a receiver GPU. So if it has to write 2 gigabytes of data over this RDMA and Ethernet and over the network to this, at the RDMA layer, there is a queue pair which is mapped to a memory region on both ends. And then this queue pair is then used over a UDP and IP and Ethernet and send over the network, right? Yeah.
Okay, just for listeners, RDMA, what does it stand for?
Remote,
Direct memory access.
remote
So,
direct.
remote
Remote.
yes.
memory
Yeah.
access. Yeah.
So DMA is like whenever whenever your CPU fetches from your local laptop's memory or RAM, and then remote is like when it can fetch or do operations or remotely on another CPU or GPU's RAM. So that's what it is. So remote direct memory access. Thank you.
Yep.
And so, so this is like, so you have a giant flow of 400 gig if you use a single queue pair on both ends. So one of the techniques is like, hey, can I extract more subflows so that, I can spray them, I can create more subflows so that the fabric can usually load balance them across all the available paths. So what this does is, hey, can we do 4 queue pairs? Queue pair is like, on both ends. In this case, what the NIC that's anchoring the RDMA does is like, okay, you have to write that same 2 gigabyte. I'm going to break it into 500 megabytes, 4 regions on both ends, use 4 queue pairs, and transmit like 100 gig 4 flows, right? And this is not new. When this is enabled, usually what happens is each queue pair uses a random UDP unique source port so that the switches, when this traffic hits the switch, it can hash, it can catch that, okay, there are 4 flows now, and it can then distribute these flows, right?
Good.
Correct. And because it's based on random, so it is like you have to hash and there is no determinism, right? What we did is very simple idea. We added determinism by we said, hey, can we, instead of using a random port, which has been done for 10 years, can we assign an IP address to each flow? And then if we do that, the beauty of that is we create this to instead of random and hashing and all those things, a deterministic routing problem. And you can now do a nice traffic engineering and pretty much carve out a lane for it throughout the fabric because the capacity exists. It's just that the load balancing, which usually hashes on a source port, takes this decision.
So in essence, what you're doing there is you're taking away using just a random number to try to load balance.
Correct.
And instead doing the work to actually map all those flows.
Exactly, right. And still using routing protocols, Ethernets, distributed routing protocols of your choice, but BGP preferably. And what that does is, so these same 4 flows, think of it as like, so now you have a deterministic flow with its own source and destination IP, and we have a pre-carved path. So let's say you have the first flow is from subnet A, the second is B, C, and D kind of thing, and then you can now use traffic engineering to pre-carve this path. Like saying that, hey, all the first flows now deterministically can take the first spine or a preferred path. So you're pretty much taking the randomness away. You say, hey, because the capacity exists, you spend money and having this 1:1 over subscription. It's just the load balancing was not, may get you in tricky situations at times. It'll work most of the time. In this case, it is predictable, deterministic thing. So if all the flows blow up, we disaggregate these flows into, so there is an important concept N. So we break these flows and as many paths you have from the leaf. So in this case, you have 4 paths through 4 spines. We'll break these subflows into 4, right? And if all the flows blow up in this case, let's say there are 8 NICs, and so each one will be a 100 gig flow now, and they will, because there are 8 GPUs, you will have 8 by 100 gig, which is, that link is 8 by 100 gig. So there won't be congestion, there won't be any out of order packets because they're not going to take any other path. It's a reserved lane for each subflow, right? Very simple idea, but very, very effective, right? So,
sorry, question. Now you are assuming that all those GPUs require the full bandwidth.
yes,
Is that always the case?
it's not, but you have to build for that case, and they are built for this. So you have, for example, like let me show you the next picture, right? Usually these are like 64 by 800 gig switch. So what we do is 1:1. What you do is because these NICs are 400, so you split the 800 gig into 2 by 400. You attach 64 GPUs, and then you have to budget that in case all of the traffic comes to the leaf, you will have 32 by 800 gigs. So that's what I mean 1:1 over subscription, meaning whatever ports you reserve for the GPU facing or the host facing, you have to have enough exact capacity towards the spine to handle if all GPUs are sending full line rate. So in this case, what we do is, as I show you, if there is a scaled 4,000 GPU topology, if you have 32 paths in this case, because 32 by 800 gig is equal to 64 by 800 here, you divide these, you break, your N becomes 32, and you will do 32 queue pairs. So that if all of them, all the GPUs here start sending traffic, it will fit nicely in a predeterministic fashion. And here you eliminate load balancing. This is pure routing because this fabric is built on BGP. And when the flows come up, it's just a look up, and there is a preferred path for each of the colors, and that's how this works. Now, the way routing works is like for each of these colors shown here, we will have a higher preferred route to a spine, and the second color will have the blue spine and so on, but we will still advertise a lower preferred route through the backup for just in case that link fails, right? Because failures are a reality. So this is how we will still advertise ECMP paths, lower preferred or backup paths, but a preferred high path. So when everything is in steady state, you have that determinism. And let's say a link or a switch fails. In that case, what happens is for this flow, which was preferred path was that spine, all the backup paths are activated, and it will do dynamic DLB and GLB across all the other paths, right, for the time being. And as soon as that link gets restored or the switch gets restored, it will immediately snap back to the deterministic forwarding.
So I just noticed you switched from earlier in the slide deck, you were using rail or rail optimized network topology.
Correct.
And with these optimizations, you've dropped back to a standard leaf and spine. And you're-
Okay, hold your thought. Yes,
Okay.
great point though. That means I'm able to explain this well. So that's a great point. Yeah, I have it covered. So I'll go over it. So now, if you see the variability, right? Like I flashed this, like so. Again, quick rehash. ECMP gets lucky sometimes over, and this is like in a controller environment, 3 consecutive runs. DLB improved it considerably, reduced that unpredictability to a narrow band. But look at this. So this RDMA-aware load balancing, what we call RLB, is consistently hitting the 373 highest performance mark all the time. Because as you see, in the design, there is nothing in steady state. It always performs.
No conflict.
There is no load balancing introduced randomness anymore, right? So so it'll keep the network running at peak performance by this design all the time, which is very desirable. And again, here I'm just showing, the DLB and RLB, some other metrics that we measured. So as you can see, in the DLB's case, yes, all the links. So again, these are all the traffic on all the links between leaf and spine. And as you can see, and we bombard with all our GPUs, the traffic using nickel test. And what we saw is with the DLB, yes, the traffic is fairly distributed over across links, but still at some point it starts causing micro congestions.
Right.
But in this case, there is no congestion because there is a reserved path and it's just a straight peak and a flat line up there. During multiple runs, we never saw any congestion metrics. So ECN and PFCs, DCQCN is primarily congestion avoidance mechanism in this Ethernet, and we didn't see any of those triggered, and no out-of-order packets because, of course, it's designed to follow a single path through the fabric anyways. Whereas in the case of the other one, and this is for rail optimized, and I'm going to come to the non-rail. Now, this is the point you were trying to say, and so in 2018-19, when NVIDIA started recommending these rail optimized designs, it was like, hey, traditional Ethernet or load balancing techniques are not enough. So we will connect them in such a way that you have rail optimized designs, and that is true because it takes off some of the load balancing requirement from the leaves. Then we said, hey, if we are achieving this kind of a performance in rail optimized, is this good enough to now go back to top of rack switch, where you have all these connections in a top of rack switch that allows you to use now copper, right? DAC cables, and DAC cables are way cheaper, less expensive. They consume very low power. They are more reliable compared to optics, and the traditional sense was, hey, performance you will not be able to get because you need to connect rail, so you have to run the longer cable. So we said, okay, let's put this to test, right? And what we found is almost this brings even non-rail, which is basically the top of the rack, brought it to almost peak performance. Because we saw, this is actual lab results from multiple runs. So really, and this is again the similar graph. There was still no congestion, no out of orders delivered for the non-rail, whereas DLB still had it. That explains it, right? So really, I summarize the benefit of this is a new, very simple idea. Uses all the components of what Ethernet's routing protocols, and just by assigning determinism to these flows and converting it into a routing problem, you have a consistent high performance, like predictable in steady state. You have in-order delivery because in steady state they will all follow the consecutive packets will follow the same path, and this is done without the need for any expensive hardware like extra NICs or super NICs or deep buffer switches and things like that. And this also delivers non-rail performance, which is highly desirable because of the properties. So,
for those of you that don't know the difference between rail and non-rail, in a rail environment, any communication from a GPU on a different rail has to travel through the PCI connection to the other GPU and then across the network. So one extra step for rail config.
Yeah. So actually, that is it. Yeah, sure. So any questions?
One more.
Yeah, sure. Go ahead, please.
When you look at scaling up, when we get into very large clusters, do you see the regular class scaling up that high? What do the topologies start to look like, or the trade-offs start to look like between rail and class?
So in the rail topology again, and that'll apply to non-rail as well. As you go like to the 5 stage, usually we start seeing oversubscription. 7:1, 5:1, that kind of, because the traffic that's traversing across that is becomes lower, and that's because also because a lot of these orchestrators have a locality property where they will try like, hey, you need GPUs of 100 GPUs or 1,000 GPUs. They will try to orchestrate the workload in a local area where you don't have to traverse that high. They're all in a cloud topology where you don't have to take more hops. So that's why you can go over subscription, and because in the case of RLB, that oversubscription we're using BGP communities and stuff, so you can still architect and factor any oversubscription on that layer where you will start assigning multiple spines to handle the same color.